Today we're going to see hydromechanical system that has a few challenges, and we would like to find out a transfer function on the system that combines a transfer function that crosses energy domains. We also would like to see that it has some difficulty in here with the derivative causality, and then we would like to obtain a transfer function explicitly using a computer generated approach. So let's talk about the system first and its problems and its solution. So here we go. We have what you have is the system here, and on the right hand side you have the bond graph model of this. Because I have set up the bond graph already, I think it'd be a good idea to talk about how it's made and to complete, because I didn't complete the causality deliberately so we can talk about it. Well, of course, this is an inertia in here that is represented by this one, right? This is an input here which is represented by this. So if you move this, and this would follow later, and this fluid inside accumulates over here, this is a cushion, right? So this is like a suspension system, because if this is air, air is compressible. If it's fluid, then possibly not so compressible, but air would do, like, this would be good like for a suspension system. So the idea is here is we have a velocity over here, a velocity over here. The difference between those two, this velocity difference in here, perhaps it might be a good idea just to give it some label here and maybe put some numbers, right? Let's just do number 1 over here, and let's do 2 and 3 and then 4 and then 5 and 6 and 7. This got 7 only. This one here, this flow here on this side, this is what I would say, you would say this is F1 minus F sub 2. So this velocity minus this is this. But this one here is actually a flow. This becomes Q here. So this TF is the one that transforms this velocity into this Q. Now remember the continuity equation that says that Q is the area times the velocity, right? This area is this one here, this one right there. Yeah, let me perhaps make a little better. Yeah, this one right here, that area. Okay, this velocity difference multiplied by the area produces the flow that goes along in here. So in here we have considered also the inertia here of the fluid. So we have it in here. We consider the fact that this is the C element that is attached to this, and also the resistor, see right there. So if we assign the causal marks, let's see what happens. Okay, we're going to assign the causal marks in here, and then we will use the red ink for that. This is the causal mark would be over here like this for the source. If we put this in integral form right there, forces this one to take this causality and forces this one to take this causality right there, and look what happens. This on the right hand side, this little friend is in derivative form now. I think it's important to think about why this happened and to think about a solution for this, and a solution that actually would make physical sense. I think we saw last time trying to solve it by hand. This derivative form is not an easy task. So I think we need to find better way to do it. And the very first thing that I would propose, not looking at the solution, but rather trying to understand why it happened. What is this bond graph trying to tell us? This bond graph is trying to tell us that the inertia effect on the mechanical side, this thing, and the inertia effect on the hydraulic side, somehow they are related. Do you see what I mean? Now let's think about whether this is true. Well, here's, if you are here and let's say you're gonna be this is your hand, you're gonna be really the strong person to shake this up and down like that. Yeah? Think about what's happening in here. Think about what's happening in here. This one, you are moving all this fluid right there, you are moving it up, right? And this other one is together with it. This is together with it. So if it is together, isn't it true that the motion of this one will determine the motion of this? Because you see, if we assign the integral causality for this one, this other one will be in derivative form. It doesn't matter which way you start, you got the problem that in the way the model is conceived right now, you are going to end up with this in integral form and the other one in derivative form. That's our problem. And what I'm trying to explain to you is that the reason that is happening is because the way we are modeling here is we are moving this and this together. If there would be a way to separate those, I think this might be different. Can we, could we find a way to do that? We would have to consider, perhaps before we consider the difference, the velocity differences for this, the fact that in this area right here, maybe the air is a little bit compressible, right? And if the air is a little bit compressible here, it would isolate this mass from this. So how would that happen? How could that happen? We need to isolate this from this. So it means that in this right here on this one, we should be able to put some sort of a compliance, or rather in here, see, to add to it right here on the side where the problem is. The problem happens, hold on for a second. The problem happens over here. This one is okay. So if we isolate this and we make it a bit compressible here, then things might go different. And so I would suggest that we try that. So let's rebuild this thing, and we have the one over here, and what I'm suggesting is we introduce a bit of compressibility in here. So let's just draw the with the same colors that we had. This is the source of flow in here, and this of course is the inertia here. We have the TF over here, but what I'm suggesting is let's consider a bit of the compressibility and put a C element in here like that. See? And then the rest we leave it like it is. And then, you know, the compressibility that we are adding doesn't have to be big. In fact, could be a small compressibility. What it's doing is fixing the equations for us. This would be the I sub F, and this I am going to say C of the pipe. Yeah? And this would be the A over here. In fact, it's transforming flow into Q, velocity into Q, so this is A. So alright, let's just do the causal assignment again to see whether we have made any progress. But does everybody understand what this C does? It considers the compressibility of this fluid over here, right here. Yeah, right there. Yeah, compressibility of the fluid right here, which is different than considering this effect on this chamber over here, right? So if this is the case, you see you have isolated the two I's. This one, you know, you put it in here, this in integral form. This forces to be like this. Yeah. And this, if we put this in integral form, makes this like this. And that allows this to be in integral form. And lo and behold, everything is cool. Okay. So I am going to perform this same operation using CAMG, but before we do that, we need to clarify what the output is going to be. What would the output be in here? Because we need to obtain the transfer function. So let me make sure we have the output over here. This is B sub M, which in this case is equal to, let's just do some numbering here. What is the number that we would enter for this? This would be F sub 2, right? And what is the input? And the input is going to be the velocity of the V sub I, which is in fact F sub 1. So the transfer function that we want really is the output F2 of S in relationship to the input. That's what we want. So we only have one input, and let's just deal with one output and see what CAMG is going to do once we put this. I'm going to put the first bond graph here, and once we put the other bond graph also. So
I have a question. If you would have put an R element instead of a C element.
So now we are about to enter the bond graph model into CAMG, and what we would like to do is to be able to come in here, and we're gonna do a new model here. CAMG prepares that for us, and then I'm gonna say, okay, look, this is the bottom is F, and then you have the 0 over here, yeah, and you get the first bond like that, and then we go to the I element over here, and then we go to the TF that we have in here, right there, and create this bond, and then we do the 1 over here, then we do this, and then we put the other I element over here, and here's where immediately you'll see, you see what happened, and then you have this R element over here, and then you have the C element over here like this. So that immediately you see this is a problem that we cannot resolve. It has derivative form. We cannot resolve it explicitly unless we basically force the system to take a derivative form. And what we have done up here is to come up with a system where we let's keep it all the way up there so that we can actually do the drawing well, with a system that resolves this problem. So let me move this up a little bit, because we actually need a delete option here. See, is on this, we are running out of space in here. I'm gonna try to make it a smaller window so that we can still have access to the bond graph model. Yes, over here, and let's see how we do here. Very good. So we need to transform this one that we have on the right hand side into one like the one is on the left hand side, but I need my delete button, so I needed to come a little farther up. Now here we go. We are going to do a surgery here. So let me show you some neat tools that ChemG has to do this. We need to put a 0 here and move these things to the right. So the first thing that I suggest is that we're gonna need to break it. Let's break this in here. Now we go here to the edit, and we're gonna move, but we're going to move a segment, meaning whatever is connected to this I, move it over here. See? And we didn't have to redraw the whole thing. And then once we make the space, we put the 0 here like this, and we say 4, and then we need to put the C element, which you have I think we might have, because we number it already. Let's see, the C element, we might have little different numbers which really don't mean anything. This one, and then you'll have like that. See, a bit of a different numbers in system, but everything is okay. This does not affect, and you can see this is totally perfectly fine. So we have resolved the derivative causality issue. We have in here objective to obtain the flow here, and then this would be the yeah, and this is F1 in here. Sorry, okay, let's just do this real quick here. go to the interface of MATLAB, and then we would let the computers, those two programs, interface with each other, and we obtain the transfer function between, in this case, F2 and F1, SF1 really. So comes up in here, and we are here on this. So over here we go and say, okay, please go and find where my variable output is, f sub 2, right? And the computer goes and it does it. And then in here you come and say, eliminate this for me, please, so that this would become the first row of the C and the first row of the D matrix, and this one in here would be 1. So once we have done that, we have another little glitch that we need to fix, that we already know. The new version of MATLAB does not like the simple command, so we're gonna get rid of it. And then you say just please run. You have defined your output. The computer gives you, this is your input, you see. These are the state variables. The output F1 is F2. So we go and it gives the matrices, does all the stuff. I will come up with the transfer function. In this case, do you see here's the numerator of the transfer function like that? Right there. And this is the denominator of the transfer function right here. Okay. More, I guess. See that command where it says simplify, it allows us to have all the powers in order. See, what I notice is that you have, let's see, no, it's okay. See, S is first power, second power, third power, fourth power. So the transfer function is right in there. If you want to see some results, what I would do is just give numbers to the parameters, like you need to do it in your lab. I need to give you the parameters, but just for the sake of testing the mechanics of this, let's just give a value to all the parameters. Let's make them 1, and then this is a 1 in here, this is a 1 over here, this is a 1.
What's the T3 by 4?
The transformer. See right there. So if you run this again, which once you in your lab or in any other example that you're running, if you run this again, it will run with numbers this time instead of with symbols, and you would have it in here. See, the matrices are numeric now, and this is the transfer function right there. And using this transfer function, the computer is going to go and derive the root locus and derive the body plot as well, the frequency response plot. So that's something that we can talk in another video here. But what we see here is, you see it gives you the body plot in here, give you the root locus plot on the bottom, and then it will give you the step response of the system, and also will give you the impulse response. So by using this approach, you have been able to obtain the computer generated transfer function. We did have it in symbolic form up here, right there, So you know what the coefficients of the denominator are made of, or what parameters influence those. We just give them some nominal values just to get something running, and then you got the transfer function here, and using this transfer function the computer gives us these plots. This one, it gives us the other plot for the impulse response and the other plot for the step input. So that shows you from beginning to end how to obtain a computer generated transfer function and how to get the results.